Okay, so today is again related to chapter number 9, gas power cycle. In the previous class, we already discussed about another type of gas power cycle, which is the internal combustion engines, that is Stirling or Ericsson cycle. Okay, and we have solved one problem also, which is regarding that proof that the efficiency of the Ericsson cycle and Stirling cycle is equal to the efficiency of Carnot. Okay, so this is the example I'm talking about. So we already discussed it. Okay, so now coming towards another example for the problem, which is 9-65 from your book. Okay, so first you have to read the statement. So consider an ideal Ericsson cycle with air as the working fluid executed in a steady flow system. Air is at 27 degrees Celsius and 120 kilopascal at the beginning of the compression, isothermal compression process. Okay, so it's mean that the beginning of compression will be at point number 3. You can explore with the TS time. So point number 3 properties are given, and then during which 150 kilojoule per kg of the heat is rejected. So the Q rejected between 3 and 4 is 150, and heat transfer to air occur at 1200 Kelvin. So it's mean that the maximum temperature is also given in your question, which is the highest temperature. Determine the maximum pressure in the cycle. So we have to find the maximum pressure, and if you just correlate with the PV diagram, you can find that maximum pressure is at point number 4 for Ericsson cycle. The network output per unit mass of the air and the thermal efficiency of the cycle. So this is the question. So you have to note down the data, then you will move forward towards the solution. Starting from the TS diagram, I hope you already know about it, that how to do TS diagram for the Ericsson cycle. I will just quickly draw over there. Okay, so flow to 2 process is your expansion process, and also it is the heat addition process. Okay, so then 2 to 3 is the constant pressure regeneration. This is your P is equal to constant for Ericsson, and then 3 to 4 is your compression process, isothermal compression, and then 4 to 1 is again a regeneration process at constant pressure, and this is your Q output. So in your question, this temperature is given because T3 is given, so it's mean that T4 is also known to us, and then the temperature at maximum point, which is highest point, is also given in your question, 1200 Kelvin, and the Q out value is also given in your question, which is 150 kilojoule per kg. So now coming towards the part number A. So in part number A, we have to find the maximum pressure. So if you just go back to the lecture, previous lecture, you can easily find that this point is at the highest pressure when we are going towards the PV diagram. And also the point number 1 is also at the same pressure. Okay, so in the part number A, we can start with the change in entropy equation, which we already see that is your from your chapter number 7. S4 minus S3 is equal to minus Q out over your TL, which is at the lowest temperature. Okay, so now the Q out is given in your question, so we can easily find this value, which is the change in entropy. So we can just say that it will be minus 150 and 300 Kelvin, and if we can solve, it's going to be minus 0.5 kilojoule per kg dot Kelvin. So now another relation we already know about it, that is your 7-31 equation, I think, or yes, 31. So S4 minus S3 is equal to Cp log of T4 over T3, because 4 and 3 is an isothermal process, so this relation will be valid for this. R log of T4 over T3. So we already see this equation in the previous lecture as well. So as it is isothermal process, so this can be eliminated. So if we can solve this equation, you can say this equation number 1 for the value of P4, because P3 is given in your question, which is 120 kilopascal. So if we can just solve it, and S4 S minus 3 we have already find this value, so you can just solve and it turns out to be minus 0.5 minus 0.287, which is the value of R log of P4 and P3 is 120 kilopascal. Okay, so now check the value of P4, it turns out to be 685.2 kilopascal. So this is the solution for your part A. If you have any question, you can also ask me. This is a simple question. So coming towards the part number B. Okay, so in the part number B, we have to find the network output. Okay, so for this, we already know that W net is equal to Q in minus Q out. So now Q out is given in your question. Q in we have to find out. Okay, and from the previous lecture knowledge, we already know that Q out over Q in is equal to Tn, which is at the lowest temperature, and Th. Okay, this is equal, and then from here we can say that your Q in is equal to Th over Tl into Q. Okay, from this equation we can easily find the value of Q in, because Th is known to us, which is 1200 Kelvin. Tl is known to us, which is 300 Kelvin. And Q out is known to us, which is 150. Okay, and if we can just solve it, it turns out to be the Q in value as 600 kilojoule per kg. Okay, and now we can just subtract this 600 minus 150, which is Q out, is from your question, and it turns out to be 450 kilojoule per kg for your W net. Okay, so this is your part number B. You can note it down, then we'll move towards the next one. So in the part number C, you have to find thermal efficiency. So for thermal efficiency, you already know that either we can say that it is equal to 1 minus Tn over Th, because the efficiency of your reaction cycle is equal to Carnot cycle efficiency. The temperature is the same. Okay, this equation is valid. So you can say that because Tn is known to you from the question is 300 Kelvin, and Th is also known to you is 1200 Kelvin. Okay, so you can just simply put the value, which is 300 and then 1200, and it turns out to be 0.75, and that will be 75% of your thermal efficiency for your Ericsson cycle. Okay. This is a solution for your 9-65 problem. So you have to note it down, then we'll move towards the next question. So here is another question. So here it is mentioned an ideal Stirling engine using helium as a working fluid. Okay, so now we have to extract some parameters for the helium, which is C3, Cv or value of K. Okay, and the gas constant R is also extracted from table A for helium. Okay, so now the pressure limit of 300 and 2000 Kelvin, so it means that TL is 300 and TH is 2000 Kelvin. And pressure limit of 150 kilopascal and 3 megapascal. So your lowest pressure and the highest pressure is given in your question, and from there you can easily say that the minimum pressure is at point number 3. If you can just correlate with your PV diagram for the Stirling cycle, and the maximum pressure is at number 1. Okay, and the thermal efficiency, assuming the mass of the helium used in the cycle is 0.12 kg. Okay, so mass function is given, the thermal efficiency of the cycle you have to find, and the amount of heat transfer in the regenerator, and the work output per cycle. So this is the question you have to note on that data and then get the solutions. So in starting from the TS diagram first, so you just draw the TS diagram. So 1 to 2 is your isothermal expansion process, and also cooling. Then 2 to 3 is your constant volume regeneration process. So V is equal to constant. 3 to 4 is your isothermal compression process, and here Q out is also there, and then 4 to 1 is again constant volume regeneration process. Okay, and your regeneration process, because you are interested in the part B, the amount of heat transferred in the regenerator. It means that we are interested that how much amount of heat is transferred from process 2 to 3 to 4 to 1. Okay, so 4 to 1 we are interested in, so we have to find the Q regeneration that is in 4 to 1 process. So this is the TS diagram. So now coming towards the solution of part number A. Okay, and before this, we have to find some property which is related to helium. So for helium, you have to just go to table A and find the value of gas constant, and R value is 2.0769 kilojoule per kg dot Kelvin. And also you can note down the value of Cv. Okay, because for the regeneration heat, we need the value of Cv because it is at constant volume. So you can just say that 0.1156 kilojoule per kg or Kelvin. This is the values per kg. In the part number 8, you have to find the thermal efficiency of the cycle. So thermal efficiency can easily be found out because the minimum temperature limit is 300 Kelvin and maximum temperature is also given in your question 2000 Kelvin. Okay, so from here you can easily apply the efficiency equation, which is 1 minus TL over TH. And by this equation you can just simply put the values 300 Kelvin and 2000 Kelvin. It turns out to be 0.85. This is the part A. So now coming towards part number B. So in the part number B, we have to find the amount of heat transfer in the regenerator. So you can say Q for 1 in we are interested in. Okay, so for this you can easily say that it is the constant volume process. So we can write that MCV T1 minus T4. This M value is given in your question. CV value you can find from table A2. T1 is mentioned in your question, maximum temperature, and T4 is also mentioned in your question. So all the parameters are known to you. So you can just simply put the values 0.12 kg, 3.1156, 2000, T4, 300, or is equal to 635.6 kilojoule. This is now Q4. This is the solution for your part number B. So you have to note down, then I will go to the next part. So in the part number C, we have to find W net. Okay, so for W net, you already know that equation is W net is equal to, you can say efficiency into Q in. So efficiency we have already found in the part is, so Q in we have to find. Okay, so Q in is in between point number 2 to 1. Okay, and you already know that it is equal to N TH, which is the highest temperature, S2 minus S1, which is the entropy between S2 minus S1. Okay, so now we have the value of N with us, we have the value of TH, but we do not know the value of S2 minus S1. Okay, so first we have to find the value of S2 minus S1. So S2 minus S1, we can easily say that is equal to CV log of T2 over T1 plus R log of V2 over V1, which is question number 7, 31 by chapter number 7. Okay, so from here, the issue is that we also don't know the value of V2 over V1. This term can easily be eliminated for the isothermal process. So how to find V2 over V1 first? So in order to find V2 over V1, we can just simply apply one relation between point number 3 and 1, because these are not an isotropic processes, so we can say that P3 over T3 is equal to P1 V1 over T1. Okay, so from here we can say that V3 over V1 is equal to T3 T1 T1 T3. Okay, so now here we have the value of T3 in your question. T1 is also in your question, and T1 is also in your question, and T3 is also in the question. Okay, and from here we can say that for the Stirling cycle, the V3, because V3 is equal to V2. If you just go back to your PV diagram, you can easily find out that these are the equals. Okay, so from here we can say V2 over V1, 300. This is 3 megapascal. Kilopascal you will just convert it to, and then 2000 Kelvin, and then 150 kilopascal for your page. From here we can find out the value of V2 over V2. So now this value is known to us, so we can simply put this value, we can say to the equation number 1 over, and get the value of S2 minus S1. S2 minus S1 is equal to 2.0769, the gas quantity for the helium, and then log of 3. And from here we can easily find the value that is equal to 2.282 kilojoule per kg dot Kelvin for the value of change in entropy for point number 1 and 2. So you have to note it down, and then I will move to the next. So if you have any question, you can also ask. Okay, so we have to find the W net, so we can easily find Q in now because all the parameters are known to us. So M, TH, S2 minus S1 in the equation to find the Q in. Okay, so from here we can just simply put the value M is equal to 0.12, TH is equal to 2 Kelvin, and S2 minus S1 we have just find from the previous slide. And in solve it, it turns out to be 547.6 kilojoule for your value of Q. So now we have to find the W net because this is your main thing which you have to find out. So the efficiency in Q in, the efficiency you have to find in the part A 0.85, and Q in value is 547.6, and from here we can simply multiply these two terms and it will be 465.5 kilojoule of the W. This is question for you 9-66. If you have any question, you can ask me or you can move on to the question and the next time. So now here's the question which you have to solve. So it is the same question which I already solved in the uh, which is 9-65. Okay, so only the data is different. So consider an ideal Ericsson cycle with air as a working fluid executed in a steady flow system. Air is at 30 degrees Celsius and 140 kilopascal. Your state properties 3 is given in your question at the beginning of isothermal compression process, during which 120 kilojoule per kg of heat is rejected. So Q34 is known to you, and heat transfer to air occurs at 1400 Kelvin. So highest temperature is also known to you. So you have to find the maximum pressure in the cycle, T4, and the net work output per unit mass of the air, and the thermal efficiency of the cycle you have to find. So you have to note down the